Welcome. So in today's lecture, what I want to do is I want to talk more about applications of integration. So last topic was how to find area between the curves. And we were talking about how if I have two functions, say f and g. Now again, this is one variation of it, but of course we have other cases, and I want to find the area in between these two. Then I subtract the area under f minus area under g. So you would get integral of, if this is a, this is b, integral from a to b of f of x minus g of x dx. So that was the idea for one. There was one application of integration. So finding the area between curves. We talked about how if the curves cross each other, or if you want to find area in between curves when the curves are actually below x-axis, or if you want to integrate it comparing with y. If you remember, we did something like this. And then we had like say f of y and g of y. And we wanted to calculate the area in between the two of them. Let's say this is c, this is d. And then this area would be integral from c to d of g of y minus f of y dy. So it was kind of a recap of what we did last time. Now, to give some dimension to our application of integration, the next application involves volume. Can we use integrals to calculate volume? Not just any volume. We need some regularities for our shapes. We need some kind of a function governing our shapes. Either the solids are very regular solids, or maybe they're solids of revolution, which is a topic, part of the topic in this section 6.2, and of course 6.3 talks about that as well. Different methods of calculating the volumes for solids of revolution. Again, that's a slightly later topic. But right now, the simple question is find the volume of a cone with height equal to say 10 centimeters and radius of the base are equal to say 4 centimeters. So I'm talking about a cone that looks something like this. This is 4, this is 10. Now we have formulas for that. Of course, you all remember 1/3 pi r square h, but I'm ignoring that I know that formula, and I try to find the volume without using the formula. So the strategy that helps us use integrals in calculating this volume is by, and again, there are different ways of thinking about this, but the way I'm going to do is I'm going to lay my cone on its, I guess, putting the axis in the middle on the x-axis. So my cone looks something like this. This is 10 units, obviously, because it's height, and it goes all the way up to 4 as the radius. Okay, and I want to calculate the area of this cone. Now, one thing that I notice, the volume of this cone, I'm sorry. The one thing that I notice is I may not be able to calculate the volume of the cone smoothly, but what I could do is I could do what with the magic we always do. We can partition our x-axis. Again, once again, we are going to have a regular partition. And when I partition it, then I can create disks. Now, again, the word disks comes up a couple of times in today's lecture, but so beware. It's not going to, the disks, and then the disks are going to have, again, I don't want to have a frustum looking disks. I want to have an actual solid edge disks. So I'm going to create these with the partition that I've been given. I'm going to have these disks that they stack up on top of each other, and they get the shape. And you get the idea, right? That's not exactly the cone, but you know the trick. We're going to first approximate the volume of the cone using those disks, the volume of those disks. And then we're going to take the limit as the number of disks go to infinity, or the thickness, in this case, height of the disks goes to 0. So we're going to do that. Okay. So the question here is, what is the volume of each disk? Well, disks are cylindrical. So the volume of each disk is really the area of the base, whatever height, the area you're going to have there, Ri, is your radius, times pi. So you get pi Ri squared. And then you multiply by the height, which in this case is going to be delta x. Pi is a constant, we know that. Delta x is the measure we're going to use. The part that we don't know that we have to figure out is how to calculate Ri. So if you look at, say, one of these disks, the one that I have initially drew in black, the radius of that disk would be the value of function at xi. What function? This function, which is a line. So if you look at it, if you just look at the equation of the line there, the value of function, that line at xi, that gives you Ri. And then you rotate. Again, I'm getting you guys used to what we're going to do in a few minutes using what we call disk method in calculating volumes. But you will have the area of the cross section would be the pi Ri squared. So Ri is really the value of function, this function, which is a line in this case, at xi. So how do I find the equation of that line? Well, I know 2 points on the graph. 10, 4 is 1 point, and 0, 0 is another point, and it's also my y-intercept. So my slope is going to be 4 divided by 10, rise over run. So 4 divided by 10, which is 2/5. And my equation of my line, f of x is equal to, or y equal to, m x plus b, in this case is 0 because it goes across the origin. So Ri is 2/5 xi. Okay. So going back to my volume formula, the volume is approximately summing up over all I, as goes from 1 to n, the area of the base, which was pi Ri squared delta x. So this is the height, the delta x part is the height. This is the area of the base. This is the volume of each disk. You have n disks, you add them together, and that gives you an approximation volume of the cone. And then, of course, we said that you can replace it with, instead of Ri, you can put 2/5 xi. Which is going to be now this is an approximation of the volume. If I want the volume exactly, I will have to take the limit as n goes to infinity of that sum. Which, if you guys remember, that is the definition of a Riemann integral. That is a limit of the Riemann sum, which gives a Riemann integral that goes from 0 to 10, from 0 to 10. Those are your A's and B, your A and B. The function you integrate is 4/25 pi x squared dx. Now, if I actually go through the different integration process, you get 4/25 pi is a constant. You get 1/3 x cubed is the antiderivative from 0 to 10, which is 4/75 pi 1,000 minus 0. So you get 4,000 over 75 pi. okay, which you can simplify this. Which you get 160 divided by 3 pi. Now, if you go back to your cone, height was 10, radius of the base was 4. 1/3 pi r square h is once again 160 divided by 3 pi. So the two are consistent. In fact, you could come up with a formula of the volume of a cone using integrals. Now I picked a simple, nice, regular shaped cone to calculate the regular solid to calculate the volume of it. Now, what if I was talking about, well, what about a pyramid? I have a pyramid with a square base. And again, once again, the height is, say, let's go with the 10 again. And one side is, say, 6. And we'll calculate the volume of this shape. Once again, you can play the same game. You can put it on the x-axis. And then you can say, well, it goes all the way up to 10. The side is 6. So instead of looking at the 3-dimension, you can say, well, I can actually just look at it in 2-dimension and say, well, I'm actually going to go from half above, half below. And 10 units in the x direction. So I'm not drawing the whole pyramid. I'm just drawing a image of it, or a shadow of it in a way. Again, the area, if I partition it in each of the partitions, you're going to have shapes that are not in nature square or rectangular, but you can turn them into rectangular shapes. And that, if I take that slice out and look at it from sideways, this is what it would look like. The thickness of it is going to be delta x. Half of the height of it is this portion. Half of the height of it. And then, of course, you double that and then square it to calculate the area of the whole square. Once again, I need to find the equation of this line. So I go from 0 to 10. This point is 10, 3. The slope is going to be 3/10. The cross-sectional area where here the cross-sectional objects were discs. Here, this cross-section areas are squares. The objects are squares, and the cross-section area is going to be the whatever the half is, you double it to get the whole side, and then you square it to get the area, the cross-section area, and then you have to multiply by the thickness. So if the slope is 3/10, then y is equal to 3/10 x is the equation of the line. And the cross-section of area is going to be 3/10 x. You double it to get the full side, full edge, and then you square it to get the area. So it's going to be 9/25 x squared. And then to calculate the volume, you have to take the volume is approximately sum I equal to 1 to n. of the cross-sectional areas times delta x, which is sum I equal to 1 to n, 9/25 x squared delta x, or in this case xi squared, because remember those are for each partition piece. And the volume is exactly limit as n goes to, yeah, we play the same game. 9/25 xi squared delta x, which is going to be limit as, which in this case is going to be just the integral from 0 to 10, 9/25 x squared dx, which is going to be 3/25 x cubed if I apply the 0 to 10, which is going to be 3/25,000 minus 0, which is going to be 3. The 25 and 1,000 cancel out, you get 40. So it's going to be 3 times 40, which is going to be 120. Now, if you had calculated the volume of the pyramid, remembering your pyramid formula, again, the volume of pyramid formula, you have 6 by 6, so you get area of the base, which is 6 squared, times height, which is 10, divided by 3. So again, you get 120. Same thing. You're not going to get a different answer because you use a different method. But again, this method of using integral is to show how that works without using the formula. And the formula can be proved using the integral anyways, like before. So this portion of 6.2, the first portion of 6.2, basically just says, if you have a solid and the cross-section areas are regular shapes, circles, squares, triangles, regular equilateral triangles, or isolysis triangles, or some regular shapes, half circles. Some of the homeworks are half circles. And you want to calculate the volume, all you need to do is you have to integrate the cross-sectional area. Area times width or height gives you the volume, and you approximate the volume or sum of the volumes and take the limit as n goes to infinity, so the partitions get very thin. So in a way, integral from a to b of ax dx is the volume. A being the cross-sectional area. Just have to work on your cross-sectional area equation. If it's a triangle, you have to figure out how the equation of the triangle would be based on where you are on the x-axis. If it's a semicircle, if it's for different shapes, you have to come up with the equation of the area for that shape at each point of the graph. Now in the next recording, I will be talking about how to calculate the volume of a solid of rotation, very similar to what I did here. Here, there's no rotation going on here. For the cone, it was kind of a rotation, but not a requirement. I could have still done it the same way I did the pyramid, but I brought up the language of rotation a couple of times just so you guys can see that where the pi comes from, although it was just area of the circle, the cross-sectional area. But next lecture, I'm going to show you guys, if I have a graph that looks like this and I rotated about the x-axis, the solid that I'm going to get, which should be symmetric, not what I have drawn, anything like what I've drawn. But if I rotate about the x-axis, what would the volume of that solid be? So that's what we're going to talk about. We're going to introduce a couple of methods of doing it. The one that's in 6.2 is disk washer method. And then in 6.3, we talk about cylindrical shells method. Only again, 6.2 is going to be on your next test, not 6.3. Okay. I hope this was helpful. And after I do the second portion of 6.2 in the next video, I will also do some problems for you guys to show you guys how to apply this machinery in finding volumes of solids.